A filter is a powerful tool in signal processing designed to separate the useful parts of a signal from unwanted noise, interference, or other signals. Imagine it like a water filter. Impure water goes in, the filter removes the impurities, and clean water comes out. Similarly, in the world of radio signals, filters help refine the messy spectrum of signals picked up by an antenna, leave behind only frequencies we are interested in. So, you may ask, why do we need filters? Real world radio signals are far from clean. Instead of just signal you want, an antenna gathers a cocktail of signals, noise, and interference. Without a filter, your receiver would struggle to isolate the desired signal from the chaos. Now, filters allows us to extract the desired signal by suppressing unwanted frequencies and reduce noise and interference, improving signal clarity. So filters act as a frequency gate, controlling which parts of signals spectrum pass through and which are blocked. Filters rely on the frequency composition of a signal, which can be analyzed using tools like the Fourier transform. Every signal consists of multiple frequencies, and filters selectively amplify or suppress these based on passband, which are frequencies that filter allows through, and stopband, which frequencies that filter blocks. In a sense, a filter adjusts the gain or amplification factor of a signal, but this gain varies by frequency. For example, if gain is 1 in the passband, which are frequencies are preserved, and if gain is 0 in the stop band, this means frequencies are suppressed. So while this is the theoretical ideal, real-world filters aren't perfectly sharp and may allow some bleed between the passband and stop band. There are four primary types of frequency-based filters, each designed for a specific purpose. Low pass filter, LPF. Low pass filter allows frequencies below a certain threshold, the cutoff frequencies to pass. Blocks higher frequencies. And the common use of low pass filter is for removing high frequency noise from a signal. High pass filter, HPF. High pass filter allows frequencies above a certain threshold to pass. It blocks lower frequencies, and the common use for high pass filter is for removing low frequency hums or interference. Band pass filter allows frequencies within a specific range to pass, blocks frequencies outside this range. And common use for band pass filter is for isolating a specific communication channel in radio systems. Band reject filter, also called notch filter. Band reject filter blocks frequencies within a specific range, allowing all others to pass. And common use for this type of filter is for suppressing particular interfering signals, like power line noise at 60 Hz. While filters sound ideal in theory, practical implementations involve some trade-offs. Sharpness. Filters aren't perfect and may have gradual transitions between the passband and stopband. Delay and distortion. Applying filters can introduce changes to the signal's timing or shape. Complexity. More advanced filters like digital or adaptive filters require careful design and computational resources. By understanding and applying the right type of filter, you can refine raw signals into usable data, enabling everything from a clearer audio to precise radar detection. Filters are indispensable in the realm of signal processing, and mastering their use is a cornerstone of radio communication and electronics. A low pass filter, LPF, is a signal processing tool that lets low frequency components pass through unchanged while reducing or eliminating the high frequency components. This makes it essential for applications where unwanted high frequency noise or signals needs to be removed. So, You may ask, how does a low pass filter work? The operation of a low pass filter revolves around a concept called the cutoff frequency. This is the diving line between low frequencies and high frequencies. The frequencies is the part of the signal that passes through with minimal change, and high frequencies the part of the signal that is suppressed or completely removed. The placement of this cutoff frequency depends entirely on the filter's design and the needs of the application. For instance, in audio processing, the cutoff might be 2 kHz to separate bass sounds from treble. In radio frequency communication, the cutoff could be at several megahertz to isolate at a specific signal band. In an ideal world, the output of a low-pass filter would look like this. Frequencies below the cutoff are unaffected and retain their original strength. Frequencies above the cutoff are completely removed as though they never existed. Let's consider a signal represented by an FFT, fast Fourier transform, showing frequency components from low to high. If the cutoff frequency is set at 2 kHz, frequencies below 2 kHz pass through and frequencies above 2 kHz are blocked. Real-world filters, however, are not perfect. There's often a transition band where frequencies near the cutoff are partially attenuated instead of being sharply stopped. Here we had some project that we created earlier, as I remember, and we used some filter. I think it was the resources and add. No, that wasn't it. Yeah, here. Now, we here in previous first AM receiver, we used something called low pass filter. The low pass filters are commonly used in audio processing, removing high frequency noise or hiss, communication systems, eliminating unwanted high frequency interference in radio signals, for electronics, like smoothing out high frequency ripples in power supplies, and data analysis, extracting long-term trends by filtering out high frequency fluctuations. Now, if we run this, why can't open the file? Yeah, however, we will create this in next lectures as well. So, this well-designed low-pass filter ensures that desired signals remain intact while unwanted components are effectively suppressed, so enhancing signal quality and usability.